Hello and welcome. Today we are going to talk about ALCN reasoning algorithm. Right. Now, before going to the formal description of the algorithm, let us start with a very small example and very easy example. And I hope that this small example will give us enough perspective to develop our algorithm. Right. Now, to begin with, let me recapitulate what we mean by ALCN, right? So ALCN stands for attributive language with complement, and added to that we have got the number restriction. So we have ALCN is equal to ALC plus N. So basically to say that this language family of description logic consists of all the constructs in ALC, and added to that we have got the number restriction, right? And what are the concept expressions that are allowed in this language? Of course, we have the top concept, the bottom concept, the atomic concept, the union of two concepts, intersection of two concepts, existential restriction, then value restriction. So these are the constructs that are allowed in ALC, and added to that we have got the at least restriction and at most restriction, right? So our goal is to have a reasoning algorithm that will try to prove or try to answer queries from a description logic knowledge base written in this ALCN formalism, right? So this is our goal. So as I promised you earlier that we'll be starting with a very small, a very simple example. So let us see what is our example. So our example is that X has a musician child. X has a musician child and X has a physicist child. So this is your given. This is something that is already there in the knowledge base, right? Now what we got to prove or answer is this: does X have a child who is both a musician and physicist? So intuitively know that this is possible, right? If X has a musician child and X has a physicist child, so X can have a child who is both musician and physicist. But our question is not exactly that. Our question is whether it is always the case. So whether it is always the case when X has a musician child and X has a physicist child, does that mean that X has a child who is both musician and physicist? Intuitively, you know that there would be certain cases where both the child, a single child would be a musician and a physicist, but there would also be a case where X has two different children, one being a musician and other is a physicist, right? So, though for a particular interpretation, the answer would be true, but not for all the interpretation, right? So, if we write this problem in the description logic term, this is how it will be looking like, right? So, how do we represent X as a musician child? We represent that with this. There exists HCM intersection and X has a physicist child. Physicist child. Now, we need to ask, does this infer or does this mean or does this imply this? And what is it? It is implying that X has a child who is both a musician and a physicist, right? So by saying this, what we are trying to mean that this is a concept expression, complex one of course. This is another concept expression. This is the third concept expression here, right? So what I'm saying here is that X is a member of HC, there exists HCM. So what do we mean by this? That X has a child who is musician. So X is some individual who has a child that belongs to a class musician, right? And this we can write again similarly, HCPX. X is a member of the class expression that says that someone has a physicist child, right? Now this says that X is also a member of this. So if this is true, so if X is a member of this and member of this and member of this as well, then this whole expression would be true, right? So this is what we got to prove. Okay. Now we have seen in the earlier class that while we will be proving something, we will be proving by the technique of proof by contradiction, and in the formal notion that is called an unsatisfiability problem. So we will convert this problem into its corresponding unsatisfiability problem version and try to see whether that unsatisfiability problem is satisfiable or not. Now what will happen if the unsatisfiability problem is satisfiable? So that will tell us that there exists at least one interpretation for which the original problem is not satisfiable, right? So this is what we will be doing, right? Now another thing that we should mention, that if for all the interpretation this holds, right? So whenever X is a member of this and X is a member of this, X is also a member of this, then it's a valid statement, right? And we know that in this case this is not a valid statement, though it is satisfactory. So what does that mean? That means that there might be an interpretation for which I can prove this, right? But not in, it will not be proven for all the interpretations, right? So whenever a particular statement is true for a given interpretation, that statement is called satisfiable under a given interpretation. But if the statement is true for all the interpretations, then we say that statement is a valid statement, right? And what we are testing here for, we are testing the validity of this statement, right? So if we consider this part, if we consider this part to be say A and this part to be B. So we can little bit write it in a little bit simpler form visually, of course, but the semantics will remain the same. Visually it looks to be simpler, right? So A implies B, right? Now how can we rewrite this A implies B? So I'm trying to flatten the things out, right? So we are having A implies B, right? And we can represent this as an equivalent to this negation of A union B, right? So I will be using this union or interchangeably, or maybe intersection and. So we can represent intersection as and I can say, so these are same thing, right? So this is your equivalent form, right? So this is your original problem. Now the unset version of this problem is basically the negation, which is equivalent to negation of A union B, and it will become A intersection negation of B. So one word of caution I like to mention here: while you are moving the negations inward, you have to be very careful about flipping the operators. So many a times there we might mm, uh, we might not do that, and that will have a very severe consequence in our subsequent steps, right? So we have to be very careful here. So given if we go back to our original problem, so what would be our original concept? We will write or designate the original concept with C0, right? We will denote the original concept with C0. So our C0 is A. What is our A? There exists HCM intersection, there exists HCP, right? And then we have got this intersection. What is negation B? B is there exists. So what is your B? B is there exists HCM intersection P, right? So the negation of this would be for all HC negation of M or negation of P. This is our original concept, right? So what we are trying to do, we are trying to see whether this is satisfiable or not, right? Now, when do we say that a concept is satisfiable? Or I'll state the reverse problem. When do we say a concept is unsatisfiable? So when a concept is equivalent to the bottom concept, that is to say, mathematically, the interpretation of C is an empty set, then it is unsatisfiable or inconsistent, whatever you say, or inconsistent. So you don't have any individual that belongs to this C, right? So the reverse one would be that satisfiable. So when we say that a concept is satisfiable when the concept expression has got at least one individual in it, right? Or at least there is one individual which belongs to this category or this concept. So mathematically, how do I write this? So there exists at least one A such that A belongs to your domain of interpretation and A belongs to the interpretation of I. If this condition is satisfied, then we say that the concept A, concept C, whatever it be, C is satisfiable, otherwise not, right? Now, with this very notion of satisfiability of a concept, we will step towards our first, we will put our first step into this algorithm, right? Now, let us talk about some more bookkeeping thing before we proceed. Now, let's say your C0 is an intersection of say three concepts: C1 intersection C2 intersection C3, right? Now, what you are trying to prove that A belongs to C0. Now, if A belongs to C0, that means A belongs to C1, A belongs to C2, and A belongs to C3, right? So I should have ideally written this, but for the sake of simplicity, I will be skipping this interpretation symbol. They will be somehow meaning the same thing in this particular context when we say that an individual belongs to a particular concept, right? Now, this is our original goal. In order to prove this, we need to see that we need to make it, in order to make it to be true, which we are trying to do, we need to make it true, we need to make it true as well, and we need to make it true, right? Now, in order to make this C1 to be true, or this A belongs to C1 to be true, now C1 can also be a complex class expression or concept expression. It might be having say C11 intersection C12 union C13. So then you have to do the same step. So in that sense, we are into a recursion, right? So you have started with the top concept, and in order to make that to be true, we are trying to prove the other concepts to be true, the other sub concepts to be true. Now, in order to prove this sub concept to be true, we are going to the next level. So our original level was C0. Now the next level concept are C1, C2, C3, and under C1 you have got C11, C12, C13, right? So you see that at every step when we started with this, we mentioned that A belongs to C, and here we are saying that A belongs to C1, A belongs to C2, A belongs to C3. So somehow you need to think about a data structure that will maintain these kind of information. We are going through different iterations, and each iteration will represent the state of our reasoning, right? Now, I have mentioned something which is basically state. State is basically at which step of reasoning we are in, right? So these states, in our case, is called a W state. So this W word comes from uh, the domain of drama and theater. Now, in many theaters, I don't know whether you have watched any theater or drama or not. There are certain scenes where everybody will freeze, right? Now, that freezing will tell you what exactly individual characters in that particular scene uh, was doing, right? Exactly here, at a given W state, we'll see what are the states of individual concepts and their corresponding individual instances, right? So that's why these particular states are called tableau state, and these tableau states are basically capturing a state of the recursion, right? So what would be our first state? You can guess rightly. So that comes from this very fact that A is a member of C0, and very simply to say C0A, right? Now how do we represent that in an interpretation graph? We have done interpretation graph in the earlier lectures. So we can represent this very simply. So for every individual, you have to draw a node, label that as the name of the individual, which in this case is A, and also you need to say which class expression does it belong to. Now it might so happen that A belongs to multiple classes, right? One particular individual can be a person and a person and male as well. Now, in this case, a particular person can be a musician and a physician at the same time. So, in that case, A would have the labels like M and P, right? So, these particular representation would be our state information, right? So, our first state in our tableau is this particular node A, and C0 is our state level, right? Not state level, the node level of the node A. That's it. So this is our tableau state T0, right? Now, what is C0? C0 is having three expressions, three sub expressions, C1, C2, C3, and they are all ANDed. So in order to make A to be a member of this, you need to make A to be a member of this, this, and this. So they will be pushed as your new goal to your system. Right? So how do we capture that? So again, we have got the same node because we don't have any other individual here. C0 will be there as it is because A is a member of C0. Now additionally, A is a member of HCM, which is valid, member of HCP, and it will also be a member of all for all HC, negation of M and negation of P, right? So this is your new tableau state. T1, right? So we derive T1 from T0 using intersection rule. So we have used a rule that if three concepts, one concept is equivalent to conjunction of multiple concepts, then this can be pushed, this can be pushed, and this can be pushed, right? intuitively this, you know that this is valid. This is a valid assumption. Now next what we can do, we need to make it true. How do we make it true? So now what we have, so forget about any other thing, forget about this and this, focus on this. Now you have this condition and you have to make these to be true. What does it tell? This tells that A has a child who is type N. How can we make it to be true? Or A has at least one child who is musician. How can we make it to be true? I can say that A has many children, say B1, B2, B3, Bn, and each of them is a musician, right? That will make this to be true, right? But is that really required? I guess no, because you just want to satisfy it minimally. Now, how do we satisfy it minimally? We just say that A has a child, maybe the child is B, and B is a musician. That's it. We don't need to say that A has got multiple children, right? So you can do that. Now that will give us, if we do that, that will give us W test state 2. I'll be doing a bit of step jumping here because the next step would be kind of similar. So here uh, we are adopting a minimalistic principle. Uh, you know that will that is related to efficiency of the algorithm, right? Now coming to this, we are done with this, we are done with this. Now this, right? Now I have to make this to be true, right? Now one idea could be, well, it has got a child, why don't I make this to be a member of P as well? I can do that, but this has got a problem. Now this will not take care of the case where A has got two different childs and one child being M and other child being the physicist. That is also valid here, right? That can be, that can also be a true interpretation for this particular statement, right? So that will not be considered here. And the second thing is, if you want to check that whether there are already some edges which are having this uh, level to be HC, you need to do a bookkeeping job, and that will reduce the efficiency of your algorithm. So that's why here the strategy is, this was our first strategy, that is the minimalistic principle, and the second strategy is will not be doing any bookkeeping and focusing the we will apply the rules locally, right? So while we are applying this rule, we forget about other things. That will help us a lot in terms of efficiency, right? Now if we apply that, what will happen? We'll have another edge HC, another child of A, and this will be your C. So that will be our new state. So what is our new state? So in the new state, we have got two new individuals added to the system. This is HC, A, M, HC, C, P. And here A will remain the same. So I'll be skipping the expressions which we have already considered, right? HC, negation of M or negation P, which we haven't really taken care of till now. So this is your new state. So let us name this to be T2, T3, because your T2 was this which we haven't really drawn. And which rule we have applied? We have applied the rule there exists rule. This is the rule we have applied, right? Now, what expression we can now focus on? So you can see that this M and P, they are in their atomicity. We cannot really do anything about it. They are complete, right? But this we need to take care of, right? So this says that if A has a child, then that child should either not be a musician or not be a physicist, right? So if we had written it very simply, say HC Q, so this means all the childs A that should have, they will belong to Q. So that is the semantics of the value restriction which we have studied earlier, right? So in order to make this to be true, we need to follow that whether there are edges coming out of A and that have labels to be HC. If that is so, the targets here, sorry, it will be, the targets will belong to the class not M, not P, right? So just trying to make this to be true, and that has to be done for all the edges that are coming out of A and having the label HC, right? So we have a new tableau state A. Everything here will remain the same. There will be no changes in the number of individuals because we are not inventing new individuals here. M, and this particular expression will be a class level of all the edges that carries HC level, right? Not of M union not of P, and this will be your C. This was P not of M union not of P. So this is our new tableau state. Now what we can do? So earlier we could not expand B and C because M and P, they were atomic concepts. Now we have non-atomic concepts here labeled with B and C both, right? So we have to take care of this. Now if we want to make B to be a member of this, we need to make B to be member of either not M or not P because they are tagged with, or they are coupled with this or symbol, right? So either B is not a musician or B is not a physicist. Here also either C is not a musician or C is not a physicist, right? Now you can see we can apply union rule here, or we can apply union rule here, right? So depending on at which branch we are applying it, so this is your P4. We have got our different threads in our reasoning algorithm, but there is subtle difference. There is a subtle difference here. So until now, we were following a single thread, right? And these were all deterministic steps. But as here we are having a or condition, either we can say that B is a member of not M or B is a member of not P. So we have a sense of non-determinism here, right? So we need to capture that, right? So let us now first consider uh, this one, right? So this we can expand like this. So let me move to the next page. So if we move to the next page, so we have got two paths which we can explore. One path is A will remain the same. I'm not going to change the number of individuals that are there in your tableau. Now we are expanding, or we are applying this OR rule. Now if we apply this OR rule, in one case we add this not M to be the level of B. That is justified, right? B is either a member of not M or a member of not P, right? So here I am writing B is a member of not M, and we just keep C as it is. And what is the alternative path? The alternative path says that B is a member of not P, right? HC is your B, M not M, union, sorry, this comma will not be there, not M, not P, and not P. And C would be remaining the same as it is. So this is small c, this is an individual, not a concept. Now we can explore another path, right? So here what we are doing, we are using a union rule. We can explore another path. Here also we have got two possibilities. So in one possibility, here we are expanding the C node, right? Or the class expression in the C node. So in one case, your C will be a member of not M, and other case C will be the member of not P. So A will remain the same. You have your B. B will remain the as it is. So your C will, with other thing, I'm just writing the minimum necessary part. I'm skipping the other part. So C was having P, of course. We have expanded not in union not P, and we are adding not in here, right? So this is another state, and we need to consider the other alternative. This is your HC, D, same here, HC, C, C will contain what? P, other things, and negation of P. So this is your T5, T6, T7, T8, right? Now we have arrived at the situation where there is no node which has got an unexplored concept expression, or we cannot apply any rule. You can see that here we have done everything what we can do, right? So every state is a complete state. So how do we define a complete state? A complete state is defined, so we need to say what is a complete state. A complete state is a tableau state where we don't have any condition to apply any rule. So no rule can be applied, right? And in addition to that, you can see that, say under B node, you have two concept expressions. One is M, the other is not M. So you have M and not M. If you can look here, you have got P and not P. So here you have a condition P and not P. So you can see that this is not possible, right? And we know that how do we represent this impossibility? We represent this impossibility as a bottom node, right? A bottom concept. So that means there is a clash. We are trying to prove a sub-expression or prove a sub-expression to be true. In doing so, we see a clash. Here we see a clash. So you need to have a condition for clash. And intuitively we know that what would be the condition. Either a particular concept X in your tableau state belongs to the bottom class, this is condition 1, and condition 2 is X belongs to C intersection not of C. If that is so, then we say that tableau states are in class. For example, this and this, right? So that means that if we follow this particular path and this particular path of reasoning, we cannot satisfy the original concept. But look at the other alternatives. In the other alternatives, you can see that you don't have any class condition. Here you don't have any class condition. Here you don't have any class condition, and as well as there is nothing more to expand, right? So these are your complete states. Complete states. And these complete states are the lead towards satisfiability of C0. and these clashes, they are your lead to unsatisfiability. Right? So what we have seen here, that for the problem in hand, the unsatisfiable version, which is your C0, is satisfiable. So we have proven that the unsatisfiability version, that is C0, is satisfiable. So the SAT version of the problem, so the original problem, for the original problem, what you can see, that there exists at least one path towards unsatisfiability, towards unsatisfiability. Because we know that if the unset version, so this C0 is an unset version, right, is satisfiable, then that says that the satisfiability version or satisfiability version is unsatisfiable. So I will not say satisfiable, I will say the original version. The original version is unsatisfiable, right? Now again, I'm not happy with this. So what we got to find? We got to find the counter example, which makes the original problem to be not valid, right? A counter example where the original problem is not satisfied. So at least one interpretation for which this is not satisfied. And how we'll get this? We'll get those from these complete states where we have got the satisfiability, because these are the particular threads which has led us to the unsatisfiability of the original problem, right? Can you see that? Now how we can derive that? So this is how we'll be deriving. We will discard all the complex expressions. We'll discard all the complex expressions, and whatever remaining with us. So here you can see that A has got all the complex expressions. So all the expressions here will be just gone, right? So whatever is remaining, so we can see that we are having two counter examples, not one, two. So let us take this one. So the first counter example. So the counter example. Or interpretation for which the original problem is unsatisfied, right? So we take out the interpretation graph from the established state. In this case, we are taking care of the uh, uh, clash free and complete established state. So this is your clash free and complete established state, and we are getting rid of all these complex expressions from the class levels of the individuals in the interpretation graph, right? So A will have no class expression because all the class expressions under A were complex, right? This will remain the same. B, we have got only one class expression which is atomic. Others are complex and non-atomic. And C, in C we have got P to be the atomic one, right? So from this, what is our domain of discourse or delta? We have got three individuals, A, B, C. What is the interpretation of M? Interpretation set M is B, because B is the only individual that belongs to M, right? What is the interpretation of P? Is C. What is the interpretation of HC? We have got two relations, right? From A to B and from A to C. So this is the interpretation. This is the interpretation that is the counter example. So this is your counter example, for which the original expression for HCM, there exists HCP. So there exists HC, M and P, sorry, MP is unsatisfiable. So as we can find at least one interpretation for which this particular goal is unsatisfiable, then I say that this is not a valid statement. So we can infer that if X has both musician child and a physicist child, that doesn't mean that they have a child who is both musician and physicist. So let us stop here today. In the next video, we'll focus on the number part of ALCN. So we haven't really talked about the N part of ALCN, right? So in order to consider N part of ALCN, we need to check what we will be doing for these two expressions, at least and at least, right? So this we'll be discussing in the next lecture.